So on Friday, you wrote down Kepler's 3 laws. We talked about Kepler, okay, and the importance of his contributions, that he proved that basically everything in the solar system orbits the sun, okay? They do so in elliptical orbits that sweep out equal areas, okay? And that if you take the period of any planet squared and divided by its orbital radius cubed, you get the same number for anything orbiting the same central point, okay? Which was essentially all the mathematical proof for destroying the terracentric model and moving towards the heliocentric model, okay, which is the sun at the center of the solar system, okay, which was, of course, mathematically supported, whereas the other was not. All right. So what we want to look at here just really quickly is a couple examples of using Kepler's law of periods, okay, to calculate either the period or the orbital radius of another body orbiting the same central point. Now, I kind of rushed through this on Friday just to make sure we kind of got to it, okay, but I want to come back to it, revisit here, okay. The term astronomical unit, or AU, right? An astronomical unit is the distance from the center of the Earth to the center of the sun. It is Earth's orbital radius, okay? We call it 1 astronomical unit, okay, just because it's easier to say that than it is to say 1.50 times 10 to the 11 meters, because that's how far it actually is, okay? 1 is much easier to plug into numbers, or into formulas, sorry, than 1.50 times 10 to the 11, and in Kepler's law of periods, we're allowed to do that, okay? So what we want to look at here is kind of proving Kepler's law of periods, and that is using that to calculate the orbital period of Mars. Okay, so we know from Kepler's law of periods that any two objects that orbit the same body, okay, will have the same Kepler constant. And the Kepler constant is arrived at by dividing the orbital period squared by the orbital radius cubed, and that will give you Kepler's constant. All right? Since that's the same for any body orbiting the sun, we can say that the period of Earth squared divided by Earth's orbital radius cubed should equal the orbital period of Mars divided by Mars's orbital radius cubed. Right? I mean, if all objects that orbit the sun have the same Kepler constant, these two equations are equal. Everybody okay with that? All right. So the question tells me Mars's orbital radius. So it gives me Rn. Do I know Earth's orbital period? How many years is Earth's orbital period? 1. Nice, right? Do I need to know it in seconds? Not now. You will later, but not now. Okay? It isn't that hard to calculate. It's just, you got to do a lot of multiplying. But, okay? And then I also know Earth's orbital radius. Its orbital radius is 1 astronomical unit. All right? So I'm trying to solve for the period of Mars's orbit. All right? So what I'm going to do is I'm just going to manipulate by bringing the radius of Mars's orbit cubed over here. All right, that'll give me the formula for the square of Mars's orbit. Then I just take the square root of that, okay? And I'm calculating how long 1 year is on Mars. Okay? So when I plug in my numbers, okay, the period of Mars is going to be the square root of 1.52 cubed times 1 squared divided by 1 cubed. Which is sweet, because what's 1 cubed? 1. What's 1 squared? 1. So really, I'm just taking the square root of 1.52 cubed. Okay? So when I punch that into my calculator, so square root of, okay, 1.52. To get the cube, you actually have to hit the math button. Okay? And it's hit 3, and it puts it cubed. Okay? So you do that if you haven't done that before. Cube root is 4. You hit 4 and you'll get cube root. All right, so a year on Mars is 1.87 Earth years. Right? So you would have a birthday just a little less than half as often. Right? And this again explains why Tycho Brahe had the results he had. Okay? By the way, A stands for years. Annum. Okay? That's the, I know it seems weird, it should be Y, but it's not. Okay? That's why Tycho Brahe saw Mars doing what it was doing in the sky. Remember, it looked like Mars would move backwards and then move forwards again. Again, that was when Earth would pass it. Okay, Earth is moving faster in a smaller orbit, so it would pass Mars, okay, and make Mars look like it was falling behind for a little while. Okay, everybody all right with how that formula works? Okay, when we get into satellite motion, you're going to see why people like using Kepler. You just have to have the right information to use Kepler. Okay, when we get into satellite motion and we're setting centripetal force equal to the force of gravity, which we'll look at a little bit today, okay, you can see that you have to use a lot bigger numbers, okay, and it becomes a little less convenient. Right? But you rarely use Kepler because rarely are you ever given, well, here's two planets that orbit the same star, and here's the information about one of them, and only one piece of information about the other. It's never that perfect, so we rarely use it. Okay? All right, let's see if you guys can use Kepler's law to calculate, to do number one, Kepler's law of periods. Okay, so we want to find, sorry, we just found orbital period. Let's do number two, okay? I want you to calculate the orbital radius of Pluto. Now, here's the thing about Kepler's law. They are giving me Pluto's orbital period in days. My units will have to match. So what do I have to use for units for period for Earth in this one? They gave me days. I have to use years. No, we have to match days. Okay, how many days in a year? 365.25. Don't forget the 0.25 because you're squaring it. If you forget it, it makes a big difference. Okay? All right. Give that one a try. I'll give you a couple minutes and then we'll do it together. Okay, so for this one here, okay, obviously two of our givens are Earth's information. Okay? And Earth's information, okay, the radius of Earth's orbit, 1 astronomical unit. Since they gave me astronomical units, that's what I'm going to use. If they'd have given me meters, then I'd had to use 1.50 times 10 to the 11 meters. All right, but in this case, they did give me the period in days. All right, so the period of Earth is obviously 365.25 days. Okay, and then they gave me the period of Pluto, right, which is 90,553 days. I don't know if that makes it sound longer or shorter than 100 and some odd years. Okay, but it's a long time for sure. Okay. All right, so I need to set this up and I need to solve for the radius, the orbital radius of Pluto. So I'm going to go period of Earth squared over orbital radius of Earth cubed equals period of Pluto squared over radius of Pluto's orbit cubed. I'm trying to get the radius of Pluto's orbit by itself. All right, so I'm going to bring it over here, okay, and then I'm going to bring everything else over to the other side because I can't solve for it when it's on the bottom. Okay, so I'm going to have the radius of Pluto's orbit cubed is going to equal, okay, the period of Pluto squared times Earth's orbital radius cubed divided by the period of Earth squared. Okay. So if I want to get just the orbital radius of Pluto, okay, orbital radius of Pluto will be the cube root, okay, of 90,553 squared times 1 cubed. I don't know why that took me so long to remember. 1 cubed, okay, divided by 365.25 squared. Okay. So when I'm putting in a cube root, okay, so I'm going to go math and then hit 4 because 4 is the cube root. Okay, so now I get a cube root, right? And then I'm going to go brackets 90,553 squared, okay, divided by, I'm not going to bother multiplying by 1 cubed, okay, divided by 365.25 squared. All right, so Pluto is 39.5 astronomical units from the sun. That means it is almost 40 times further from the sun than Earth is. Okay? That is a long way. Right? Now, you'll notice that there are 5 significant digits there. Okay? Why? Isn't 1 astronomical unit going to contribute? It's a constant and it's a counted value. Okay, 1 astronomical unit. Okay, 365.25 days is a measured value. Okay, that has 5 significant digits. So does this. Okay, they both have 5 significant figures. The 1 does not. Okay. All right, weird one but true. Okay, everybody all right with Kepler? Like I said, it's not something you're going to use very often. It's certainly not something I'm going to make like a unit exam 5-mark problem on. Okay, if you know how to use it, you might be able to use it in certain situations, but you can always use satellite motion, which is what we're going to start on tomorrow. Okay, today we got to talk about gravity and what makes gravity work. Okay, that's what we'll be looking at today. So if you guys can find in your notes lesson 9 on universal gravitation, that is what we're going to be talking about here right away. Okay, so you have me for Physics 20, not Mr. Dickey. Today's the day you're going to be thankful for that. There aren't too many other days we'd be thankful for that because he's really, really good. Okay, but today's the day you're going to be thankful because I'm not going to make you really, really uncomfortable like he does. Okay, when he teaches this lesson, he makes everybody in the class look at someone near them, right in their eyes, and say this: I'm attracted to you. See? You're squirming right now, and I'm not even making you do it. Okay, but it's true, not romantically. Okay. But gravitationally, it's true, okay? Because anything that has mass can generate a gravitational field and attract things to themselves. All right? Now, our gravitational fields are puny, okay? If we were out in a, interstellar space where there was no other masses around, we could barely attract a piece of dust towards us from a meter away gravitationally. Okay, that's how little gravitational field strength we can produce because our mass is tiny, right? But what we do live near is a really, really large mass, Earth. Okay, Earth is very, very, very big. Okay, and as a result, can generate considerable gravitational force. Okay, enough that we can keep the moon in orbit, and the moon is big. Okay, like in terms of moons, we have one of the biggest moons in the solar system. In fact, lots of astronomers consider the Earth-Moon system to be a double planet system. Okay, because the moon is actually so close in mass to Earth. Now, I say so close, we're talking astronomical values. Okay, the moon is several thousand times smaller than the Earth in terms of mass. But okay, when you look at other moons in the solar system, okay, their mass ratio compared to their orbited planet is much, much smaller. Okay, so most of the moons that orbit, like Jupiter and Saturn, most of those, with the exception of a couple, are much, much smaller than our moon. But they're orbiting something huge, okay, compared to the Earth. Okay, so the Earth has a very large moon for a planet of its size. All right, so looking gravitationally speaking, what are some things that can affect gravitational attraction force? Okay, now, this is another weird thing. Remember that whole story about Newton's apple? Right? Newton discovered gravity because an apple hit him in the head? That's all a lie. Okay? That didn't really happen. Okay? It was a way that he used to explain how gravity worked. Okay? His explanation is the part that gets overlooked. He said the apple and the Earth move towards each other because of the gravitational attraction. And he's right. Okay? You are just as attracted to the Earth gravitationally as Earth is to you. The difference is you're tiny and the Earth is massive. Okay? So we don't notice the Earth's attraction to us. Well, actually we do. Okay? But it just feels like the Earth pulling on us. Okay? It doesn't feel like we're pulling on the Earth. Okay? When I'm standing here, I don't feel myself pulling the Earth towards me, but I am. And that's why I feel that force on my feet. Okay? It's not just that the Earth is pulling on me. We've simplified it to be like that up until this point in the course. But in actual fact, I'm pulling the Earth towards me, and the Earth is pulling me towards it. There is a mutual attractive force between our masses. The same is true for the Earth and the Sun. They are mutually attracted to each other. Okay? Earth and the Moon, same thing. Mutually attracted to each other. And that's actually what causes the orbits that are what we see in reality versus what we picture. Okay? We picture the Earth going around the Sun in this little elliptical orbit, okay? And that the Sun is just sitting there, and the Sun never moves. Except the Sun does move. Okay? The Sun wobbles back and forth all the time because it's being pulled by all the planets that orbit it, Earth included. Okay? This is what they're using to detect all the planets that are extrasolar planets. Okay? All the ones that orbit other stars. Okay? They're using this idea to detect not only the presence of those planets, but also to get an idea of their mass and their distance from their parent star. Okay? Once they've located them by that means, then they train the Kepler telescope on them and watch them transit in front of their stars and stuff like that. Okay? But up until then, what they do is they watch the star and they see what happens to it. Okay? And what happens is the star will shift its colors slightly. Okay? When it's moving towards us, the wavelength of light that we can detect with X-ray telescopes becomes more blue. Okay? And when it moves away from us, the wavelengths of light we detect become more red. It's called the Doppler Shift. Okay? And so we detect that these stars wobble back and forth. Okay? If the star is wobbling, then we know there's something around it that's pulling on it. Okay? Other planets. In some cases, those planets are very big. Okay? And they can make the star wobble a lot, especially if they're very close. I don't know if you've heard the whole like super Earths and the big gas giants that they've discovered around other stars. Okay? Some of them are incredibly massive. They make Jupiter look tiny. Okay? And they can cause a lot of wobble because not only are they bigger than Jupiter, they're closer than Mercury. Okay? And so they can cause a significant wobble in their parent star. Okay? And that's all because of this mutual attractive force that exists between any two masses. Okay? If we look at the Earth's orbit, okay, as it goes around the Sun, okay, we picture this. Right? Here's the Sun, and the Earth's orbit looks like that. Maybe it's a little more elliptical and better drawn than that, but that's essentially what it looks like. Okay? In actual fact, that's not what it looks like. It's that shape, but it actually looks like this. Okay, why does it look like that? What's making the Earth wobble back and forth? Not the Sun. It orbits the Sun. The Moon. Okay? The Moon makes Earth wobble back and forth. Okay? If we didn't have the Moon, our seasons would be even more wild than they are now. Okay? Because we would wobble back and forth on our axis even more. Okay? That would become even more pronounced. Okay? But because we do have the Moon, we actually wobble in the orbit instead. Okay? So if Earth is here, when the Moon is here, okay, Earth gets pulled towards the Sun. Okay? When the Moon is out here, Earth gets pulled away from the Sun a little bit. As the Moon orbits the Earth every 28 point whatever days, okay, the Earth gets pulled in different directions. Okay? And this happens obviously because the Moon does this. Okay? Earth is being pulled in lots of different directions as it orbits. So its orbit tends to wobble back and forth considerably due to all of this. Okay? All right. So things that can cause gravity. Things that can affect gravity. Okay? Things that can affect gravity. Boy, that's different. Seems like there could be a better time for that. Okay. I lost my train of thought. It's not because I'm old, it's because I'm distracted. Right, things that affect gravity. Okay, the cause of gravity is mass. Anything with mass causes gravity. Okay, things that can affect gravity are the two masses that are interacting and how far apart they are. Okay, if the Moon was closer to the Earth, would there be more gravitational interaction? Yes, there would. Okay, think about what the Moon causes on Earth. What does the Moon cause? tides. Okay? Imagine now the moon is twice as close to the Earth. Okay? It would look a lot bigger in the sky, and tides would happen, A, more often. High and low tides would be way more than probably twice as many in a day. Okay? And they'd be way bigger. Right? So imagine you're in like the Bay of Fundy. Anyone ever been there? Nova Scotia? Bay of Fundy? Biggest tides in the world. Okay. Like I was there once and it was like crazy. I followed the tide out. I walked out with it. And then I nearly got swallowed up because trying to walk back in on the tidal sands is really slow. And the water came in faster than I could move. I was like swimming by the end. Okay, it's crazy. Okay, but it's huge, the tidal difference. It's like over a kilometer in some places. So imagine now, the moon is twice as close. So now that water goes out twice as far, but comes in twice as far. Imagine you live in any coastal city and suddenly the moon is twice as close and the tides are twice as big. You're going to be under water, okay? Half the time. It would be bad. Right? But the moon used to be a lot closer. Okay? Used to be a lot closer to the Earth. Right? And tides were much bigger and much more frequent. All right. So for an object to have weight, it has to interact with another object. So there have to be two masses, okay, interacting. Because weight, according to what we know, okay, is not as simple as this. We write that because it works on the Earth's surface. But in actual fact, it's this. Okay? The force of gravity is the universal gravitational constant, which is just a number that's on your formula sheet, okay, times the two masses divided by their separation distance, or radius, squared. Okay? So, the two things that can affect the weight, okay, or the force of gravity between two objects is how heavy the two objects are, which is why if I go to the moon, I weigh less than I weigh here, okay? And how far apart they are. Which one has a bigger effect? The mass of the objects or how far apart they are? Look at the formula. Which one do you think mathematically would be more important? Which one's squared? Right, okay, exponential relationship there, right? Okay, if I get twice as far away from the Earth, I will not weigh half as much, I will weigh 1/4 as much, okay? I move 3 times further away from the Earth, I weigh 1/9 what I would weigh on the Earth's surface. Okay, so there's an exponential relationship, inversely exponential, okay, between separation distance, r, and the force of gravity. Okay, so here's the weird thing about Earth. Okay, if I am standing at sea level at the equator and I weigh 70 kilograms, okay, I will weigh at the equator 684.6 newtons. Okay, 9.81 times my mass, 684.6. Okay, if I go to sea level at the North Pole, so I'm still at sea level, mind you, but now I'm at the North Pole, I weigh 688.3 newtons. I'm still on Earth. I'm still at sea level. Why am I heavier? What?
The Earth isn't a perfect circle.
Right. The Earth's not a perfect circle. It's slightly ellipsoid. It's not flat. Okay? If everyone was flat Earth crazy people, Earth is not flat. Okay? That's crazy talk. Okay? Absolutely crazy talk. Right? Then there's different levels of crazy, like that guy that launched a rocket to try and prove the Earth was flat. Okay? We've already launched lots of rockets and they all proved the Earth was round. Okay? Totally round. But not totally round. Slightly ellipsoid. Okay? So the reason that I weigh more at the North Pole is at the equator, I'm further from the center of the Earth than I am when I'm at the North Pole, because the Earth is squished slightly. Okay? Has to do with the way it formed. Right? When it formed, it was a molten ball and it was spinning. Okay? It spins a lot faster at its equator than it does at the pole, so it naturally kind of stretched out a little bit. Okay? So I weigh less at the equator. Okay? If I go to Chicago okay, I would weigh 686.2 newtons, right? So Chicago's kind of a mid-latitude city, right? I'm still going to be closer to the center of the Earth there than I would be at sea level if I was at the equator, okay? I'm kind of halfway between the two if I'm in Chicago. Here's the weird one. If I stand on the highest point on the Earth's surface, where theoretically I should be furthest from the center of the Earth, I'm not. I'm actually closer to the center of the Earth, standing on the top of Mount Everest, than I am twinkling my toes in the sand at sea level, at the equator. Okay, that's how oblong the Earth is. Okay, and Mount Everest is like a pimple, okay, on the surface of the Earth. Okay, the Earth is like, from a distance, perfectly smooth. Okay, all those little things, all those mountains and everything, even Mount Everest, they're barely noticeable in terms of scale. Okay, so standing on the top of Mount Everest, I'm closer to the center of the Earth than I am sitting on a beach at sea level at the equator. Crazy, but true. Okay, all right. If I go into low Earth orbit, so if I'm on the International Space Station, I still have weight. I weigh 647 newtons. Okay. If I didn't have weight, I wouldn't stay in orbit. Okay? I still have to be attracted to the Earth, even in orbit, or I wouldn't stay in orbit. I'm using gravity as a centripetal force. Okay? I'm still having a gravitational interaction between me and the Earth, even in low Earth orbit. In high Earth orbit, which would be way out here, we would call this geosynchronous orbit. Okay? That's where all of our communication satellites are. Okay? I would weigh a lot less. 15.5 newtons. All right? Yes, I'm a lot further away, but remember, the effect of separation distance is exponential. Okay? So the further away I get, I'm going to weigh exponentially less. Okay? So distance does not make you more attracted to something. It makes you less attracted to something. Don't try and apply that to long distance relationships. It does not apply. Okay? This is not a sociological principle. Scientific principle. Okay? All right. Everybody following me so far? Okay. If I go out and I'm on the moon, okay, or not on the moon, but in the same distance from the Earth that the moon is, I'm still attracted to the Earth. I still have a gravitational interaction, a weight due to the Earth. 0.19 newtons, it's pretty small, okay, but I still have it, right? If I go to the edge of the solar system, now it's getting pretty ridiculously small. Okay, 10 to the minus 8 newtons. I'm really not that attracted to the Earth out there. Okay, mostly the sun, okay, but not really the Earth because I'm so very, very far away. Okay. All right, making sense? So the big thing to remember here, guys, is weight is dependent on your surroundings, and any two masses will exert, and here's the key, mutual attractive force upon each other. Okay, that force is mutual. It is not one on the other. It is a mutual force between the two. Now, if Earth were to just double in mass suddenly, how much more would I weigh? Okay, looking again at the formula. If nothing else changes, but suddenly Earth's mass doubles, how much more do I weigh? Okay, imagine everything else in this formula is 1. So in the first situation, it's 1 times 1 times 1 over 1 squared. Okay, in the second situation, I double the mass of the Earth. 1 times 2 times 1 over 1 squared. How much more do I weigh? 2 times more. Okay, mass has a linear relationship. Any change in mass will cause a linear change in weight. Any change in radius, or separation distance, will have an inversely exponential effect. Okay, I double my separation distance, there's 1/4, okay, of the gravitational attraction. Okay. All right. So, Newton studied these attractive forces. This is Newton's universal law of gravitation. That sucks for Cavendish. Remember I mentioned Cavendish's name the other day. Newton never made this formula work. Okay? Newton was never able to make this formula work because he was never actually able to measure the gravitational force between two objects, because what always interfered? If I just want to measure the gravitational attraction between these two objects, okay, all right, I'm going to let them go, okay, and I'm going to measure the gravitational attraction between them. Ah, crap, why didn't that work? Only thing I can measure is the gravitational attraction between those objects and Earth. Earth always interfered with every experiment he tried to run, okay? He had the same problem. All he could measure was the Earth, okay? And the interaction with the Earth, because Earth is massive and its gravitational field envelops us. And he just couldn't figure out a way to actually measure, okay, and record this gravitational force. Okay? So he knew that the masses that were involved and their separation distance mattered. Okay? He knew that. And he knew that bigger masses had bigger interactions, or at least he was able to kind of come up with that idea. Okay? But was never able to prove it mathematically. Okay, it wasn't until a guy named Cavendish came along, okay, and Cavendish built this apparatus. I'm going to show you a video of this in a minute because I finally found one. Okay? Cavendish built this thing called the torsion balance. Okay? The torsion balance makes Earth's gravitational force perpendicular to the forces you're trying to measure. Because it's perpendicular, it has no vector component that's acting in the same plane as the one you're trying to measure. So he essentially eliminated the effect of Earth. Okay? What he did is he built this balance. Okay? He had these two big lead spheres, these big massive weights. Okay? And he had them just on this like pivot. Okay? And they just sat like this. Okay? He hung this other thing from the ceiling, and he had it made out of wire, okay, which he called the torsion fiber. Okay? Everything has like a tensile strength, and it takes a certain force to twist them or change their shape. Okay? That's what tensile strength means. Okay? So this torsion balance was going to basically measure the force required that would twist this wire. Okay? This wire would twist because there would be a gravitational attraction between the masses. And it would rotate so that the two small masses would move towards the two big masses. Okay? And then there would be this force that would torque on the torsion fiber. Okay? That's why it was called a torsion balance. All this stuff was balanced, okay, and allowed to move freely and independently of Earth's gravity. Right? So what he didn't have a laser, obviously, because this is like the 1700s. Okay? But he took a light beam, okay, just like through a hole in a piece of paper, okay, and he shot it towards the mirror that was attached to the torsion fiber. Okay? And what happened was, as this thing started to move, he was able to measure the angle it changed by. And then he was able to use that angle to calculate the amount of force that was in the torsion fiber, and thus the gravitational force between these two objects. Okay? Now, that was important because it allowed him to calculate part of this formula that Newton never could. He was able to measure this. Newton could never do that. And as a result, he was able to figure out what the universal gravitational constant was. Okay? Whenever Newton tried to make this work, it seemed like everything in the entire universe was way too heavy. Okay? The numbers he would get were ridiculous and would crush us. Okay? And that's because he didn't have this universal gravitational constant, which just happens to be this number. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We never use the units for it, so I think that's right. Okay? Is that a small number? 10 to the minus 11? It's really small. Okay? But it makes the calculation of the force of gravity possible, okay, where Newton could never do that. Okay? He would get these massive numbers because he wasn't multiplying by the gravitational constant. All right, so that's the torsion balance. Okay, that's effectively how it worked. I'm going to show you a video on that here in just a sec. Okay, so we got the universal gravitational constant. That number is on your formula sheet, okay, under other useful constants, so on the back. Okay, it's extremely small, so gravitational attractive force between two objects like your body and a baseball is so small that it goes unnoticed. Okay, now here's the other thing we have to be aware of: this inversely exponential relationship, okay, between radius or separation distance and the force of gravity. So we got force of gravity here on the y-axis, and we've got separation distance on the x. And you can see that as x gets bigger, the force of gravity gets exponentially smaller. Okay? So doubling the distance 1/4, tripling the distance 1/9, okay, and so on and so on. All right, so let's have a look at this video. Okay, so looking at this formula, okay, the Newton's universal law of gravitation. We're going to do this example here together. We're going to calculate the weight of a watermelon, okay, on the moon. Not that anyone would bother taking a watermelon to the moon. It's not an effective means of taking mass. Mass is expensive to take anywhere, okay? So we want to calculate the weight of the melon on the moon. So the givens we have are, okay, the mass of the melon, right? We're going to call that mass 2. Okay, it's 0.65 kilograms. We have the mass of the moon, which we're going to call mass 1. Okay, and it is 7.36. It is 7.36 times 10 to the 22 kilograms. And the distance from the center of the moon to its surface, on average, okay, or in other words, the separation distance here, is 1.74 times 10 to the 6 meters. Okay, that's a lot. It's like 1,700 kilometers. Okay, the radius of the moon is 1,700 kilometers. Okay. Comparatively, the Earth is 6,370 kilometers in radius. Okay, so bigger than you probably thought. All right, so I've got these numbers. Now I want to calculate the weight of the melon, that is the mutual gravitational attractive force between these two masses. So I'm going to take big G, the universal gravitational constant, multiply it by the two masses, and then divide by the separation distance squared. What do you suppose the most common mistake is when using this formula? Forgetting to square a radius. Absolutely. Guys, if you're using this formula, the answer should make sense. So if I'm talking about something sitting on the Earth's surface and you're getting a number that's like 10 to the 7, you did something wrong, like forgot to square the radius when you divided. Okay? Your answers should always make sense when you're doing this. Okay. The weight of this melon, okay, should be small. Agreed? Right? I mean, it's not a big thing, and it's on the moon. 1/6 of what it should be here on Earth. All right, and I just say that because I want you to think about what kind of number would be reasonable. Okay, on Earth, okay, this melon would weigh about 65 newtons or something like that, somewhere 6.5 newtons. It would weigh 6.5 newtons or so on Earth. Okay, not very heavy. Okay, so on the moon, 6.67 times 10 to the minus 11. That's big G. Okay, times mass 1, the mass of the moon, 7.36 times 10 to the 22, times the mass of the melon, 0.65, divided by their separation distance, in other words, the radius of the moon, 1.74 times 10 to the 6 squared. All right, is punching this into your calculator going to be a pain in the neck? It is. Lots of brackets. Okay, are going to be necessary here because you got all these exponents that you have to deal with. All right, so when we're putting this in here, we're going to have in brackets, I'm going to have two sets of brackets for the top. 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22 times 0.65. All right, so I've enclosed the top in brackets. Now I'm dividing that by the bottom, which is going to be 1.74 E6 squared. All right. So I said on Earth, this thing would weigh about 6 to 6.5 newtons. On the moon, it weighs 1.1 newtons. Is that about 1/6 of its weight on Earth? So that's a reasonable answer. Okay? So the weight of this melon on the moon is 1.1 newtons. Okay? Everybody all right with that? terrible difficult there? And we're just plugging in numbers, right? Okay. Now, manipulating this formula, also not all that difficult. Everything's either multiplied or divided. So if we're wanting to, solve for r, we'd bring r over to the other side and then divide fg over. And we can solve for the individual masses, okay, stuff like that. It's just algebra. Okay. All right, so that's what we just did. Okay, so Newton's first law says that any body, planet, star, meteor, etc., is going to remain in motion unless acted upon by some unbalanced force. Okay, so if we were talking about, let's say, the moon being this dot here, okay, and this being the Earth, according to Newton's first law, if there was no gravitational attraction between the moon and the Earth, the moon would just go straight on by the Earth. Okay, but there is an unbalanced force. The force of gravity. Now I'm going to explain to you how gravity acts as a centripetal force. Okay? The moon is moving very fast. The moon wants to obey Newton's first law and travel in a straight line. But gravity pulls the moon towards the center of the Earth. In other words, it falls directly towards the center of the Earth. But while it's falling, it's still got all this velocity. But it's always falling. But it's got all this, you get the idea, I'm not going to keep trying it. Okay? But it's got all this velocity, it keeps falling. All this velocity, it keeps falling. Okay? What happens if I just do this? The combination of the moon's inertia and the Earth's mutual gravitational attraction to the moon produces an orbit that is roughly circular. Okay? Now, this orbit is not perfect. Okay? It's a little bit elliptical, and it's actually getting bigger all the time. The moon moves away from the Earth a little bit every year. Okay? And that's because of the way the moon formed. Okay? Our current theory, which is supported by a lot of evidence, okay, of how the moon formed was by a massive impact. Okay, early on in the Earth's history with an object about the size of Mars. Okay, so Earth was a little smaller then, okay, and was impacted by this Mars-sized object. It was not a straight-on impact. Okay, it was more of a glancing blow. Okay, that impact was enough to essentially annihilate the impactor. Okay, that would be the Mars-sized object. All right, basically just crushed it. Okay? It basically just blew into a million pieces, or probably trillions of pieces, or whatever. Okay? But that impact also generated an incredible amount of energy on Earth and effectively liquefied it. Okay? Turned it into all liquid molten rock. Okay? Now, there was a big debris field, okay, surrounding the Earth for millions of years after that impact. A lot of that debris just fell to Earth. Okay? But some of it accumulated into a separate body. Okay? And then as it cooled, it congealed and formed the moon. Now, at this point, the moon is not this far away. The moon is like right here. Okay? The moon is super close to the Earth. Okay? So it would have looked huge in the sky. Imagine like science fiction movies where they have this big moon in the sky. That's kind of what it would be like. Okay? The moon would have been a lot closer, and thus its gravitational force on the Earth would have been much, much greater. Tides would have been huge, which was actually very important for the formation of early life. Okay? Having, water supplied and having always bringing in fresh nutrients. Tides bring in all kinds of nutrients from deeper water. Okay? That would have been very important for some of the first life that formed, okay, within the Earth. Okay? As the water would move up onto the Earth's surface or onto the dry land, it would absorb nutrients and minerals and things like that and bring them back into the deeper ocean because there's this constant circulation. Okay? So anyway, the moon was much, much closer to the Earth. But because of the initial velocity of the impactor, that debris field, even after it congealed, still maintained some of that initial kind of inertia. And ever since that impact, okay, the moon has been slowly spiraling away at an incredible pace of about 2 centimeters a year. So there's nothing you have to worry about. The moon is not going to fly away in our lifetime. Okay? 2 centimeters a year over 4.5 billion years adds up, though. Okay, it has moved a long way since that time, right? But it is moving ever so slowly away from us. Okay, and we actually see that in a few other places as well. Mars, for example, has 2 moons. Okay, and those 2 moons, Deimos and Phobos, fear and panic, the companions of war, okay, are actually moving. One is falling in, and one is moving away. I can't remember which one now. Okay, so one is actually going to fall into Mars, and the other is actually going to fly off. Not anytime soon, okay, but that's what's happening with those. All right, everybody okay with that idea there? So gravity can act as a centripetal force. Okay, that's how orbits are achieved. All right, so that's just the explanation we just went through. All right, so let's do this. Let's say that I want to calculate how fast the moon is moving in its orbit around the Earth. Okay? So if I want to do that, I have to understand that gravity is acting as a centripetal force. Okay? Up until now, we would have just done this. Why won't that work now? It's what, sorry? Partially, it's not moving in a perfect circle, but what number do I always use here for G? 9.81. Does that apply where the moon is? It does not. That's why I can't use this formula. Okay? I can't use that formula because I don't know what G is. G changes depending on how far away I am. This formula, on the other hand, takes that into account. Okay? Still force of gravity, but this one works anywhere. Okay? Doesn't matter how far apart the masses are or whatever, it's going to work. Now, instead of writing mass 1 and mass 2, I probably want to use letters that make more sense. Okay? Like mass of the Earth and mass of the moon. There's a mass on the other side. Which one is that? Anytime we've done this, used this formula, the m we put into mv squared over r is the mass that's moving, right? Or that's moving in the circle, the orbiting mass, right? Okay? Anytime we've ever used that formula, it was a banked curve, it was an unbanked curve, it was always the mass of the object that was doing the circling. Okay? In this case, the object that's doing the circling is the moon. All right? So the m on the other side is always going to be the orbiting mass. And what's going to happen to that orbiting mass? It's going to cancel. That's an important thing to understand. It cancels because all masses fall at the same rate. Here on the Earth's surface, all things fall at 9.81 meters per second squared. That idea doesn't change just because of how far away I go. Okay? All things still fall at the same rate. It's the rate that changes. All right? So it doesn't matter whether I have the moon out at the moon's distance or a basketball. It'll have to move at the same speed because that speed is not dependent on its mass. It's dependent on the Earth's mass and how far apart they are. Okay? All right, so I want to solve for V. What do I have to do with this R? Multiply both sides by it. All right, so I bring it over here. What happens to the R and the R squared? They cancel. Just the squared, though. All right, and we just said the mass of the moon was going to cancel because if I divide both sides by mm, they'll cancel off. All right, and I want to get V, not V squared, so what do I have to do to both sides? Square root. Okay. All right, so now I can figure out what the speed of the moon is as it orbits the Earth. All right, so first number, 6.67 times 10 to the minus 11, big G. Okay. And I'm multiplying that by the mass of the Earth, which is on the back of your formula sheet under other useful constants. It is 5.98 times 10 to the 24 kilograms. Okay? It's big. And then I need to divide that, okay, by the radius between them. Now, also on your formula sheet is the average Earth-Moon distance. 3.85 times 10 to the 8. Yeah? Oh, it's 3.84 on our formula sheet? 3.85 on it. Yeah, in the textbook it's different. Oh, weird. Okay, we got to go with what our formula sheet says. 3.85. Okay, not going to make that big a difference. All right, so I'm going to divide by that. Okay, once I plug all that in, I'm going to get the speed of the moon as it orbits the Earth. All right, lots of brackets. Okay, brackets are super important here. I actually need 3 of them. 6.67 e negative 11, so there's big G, times the mass of the Earth, 5.98 e 24, bracket, bracket, okay, divided by, in brackets, 3.85 e 8, end bracket, end bracket. Okay, lots and lots of brackets. So the moon moves at 1,017 meters per second. That's 1 kilometer per second as it orbits the Earth. Is that pretty fast? It is. Okay. It's quite fast. Everybody okay with that one? That's your first satellite motion question. That's what we're going to be starting tomorrow. Okay, satellite motion, but that's your first example of satellite motion. Okay, anytime you have a satellite orbiting something else, Fc is equal to Fg. Gravity is providing the centripetal force for all satellite motion. Okay, so looking at a few things here. Okay, it's kind of hard to see this picture here, but okay. This diagram shows every space mission ever launched from Earth. Okay? There's a lot of little lines. Okay? The most often visited body is the moon. Okay? More missions have been launched to the moon than anything else. Now, if you look at the color scheme here, it's a bit hard to see. Okay? But what we see here is colors, okay, like the color scheme goes like this. There's light colors, like the light red, and then beside it is dark red. Okay, there's dark red, light red, dark red, light red. Okay, so dark red, failure. Light red, success. Okay, and you notice here, are there a lot of dark lines? Okay, so there's lots and lots of dark lines. The different colors are just the different countries that launched the missions. Okay, red I believe is the U.S. or NASA. Okay, so that's why you see mostly the red. And early on, you saw a lot of yellow, which was the Soviet Union. Okay, and then we've got green, which I think is the European Space Agency, and then I think there's China as well in there. Okay, but anyway, these are all the different missions that were launched. Okay, from Earth to different places, and we can see that it's not a super easy thing to undertake to send something to another body in our solar system. Gravity can be both helpful and destructive when we're planning out these kinds of missions, okay? Especially to the outer solar system. Just to get something into orbit means having to overcome Earth's gravity, which is considerable, especially considering how much mass we're trying to put out there. But we have to give it enough speed that it can escape Earth's gravity. It's called escape velocity. That escape velocity is considerable. Okay, so usually we can only make rockets that are so powerful. Okay, enough to get things out of Earth's gravity, but if they're going to go any distance beyond Mars, they need some help. So what we use is the gravity slingshot technique. Okay, you may remember this. They used it in The Martian. Okay, the astrophysicist guy was doing the calculations. Okay, and he was talking about he did the thing with the stapler and the pen, right? and all that kind of stuff, showing them the gravity slingshot, okay, that they were going to use. So a gravity slingshot simply does this. Okay? I want to get to Jupiter, but I don't have enough fuel to get going fast enough to get there. So what I do instead is I actually launch towards the inner solar system. Okay? And I do a gravity slingshot around Venus. And then I get accelerated. So Venus pulls me in gravitationally, and then at the last minute I use a little bit of fuel to change my course, and I go off at a different angle at a greater speed than I came in at. Okay? And that's the gravity slingshot maneuver. So I get slung around the planet and shot off in a different direction at a greater rate of speed. So all the Voyager missions, New Horizons, all of that went to the outer solar system, all used the gravity slingshot. Okay? It got them going really fast, okay? And it allowed them to kind of stop at different places. New Horizons only did this once. Okay? The Voyager probes, they wanted to go to every planet in the solar system, so they used it basically every time. Now, that gives people the idea that the planets are all nicely aligned in a row, and they're so not. Okay? The main reason why not all of the missions have gone to all the outer planets is sometimes they're on the other side of the sun, and there's just no way to do a gravity slingshot that's going to send you clear across the sun again, okay, to the other side. Plus, the mission would take forever. Right? So it's very difficult to do those calculations and get them to work. Okay? The other thing that really wreaks havoc with space missions is getting to the other planets and the conditions that are there. Okay? If you look at Venus, you can see there's a lot of dark lines around Venus. Okay? Getting to Venus, not that difficult. Landing on Venus, big problem. Why? What's Venus like? Yeah, if you can imagine what hell is like, that's Venus. Okay? Inside, like at the surface of Venus, it's hotter than your oven can get. Okay? That massive greenhouse effect that's going on there, okay, makes it so hot, okay, that it's hotter than the inside of your oven, but that's only the half of it. Venus's atmospheric pressure is 100 times Earth's. Okay? That's basically more pressure than a submarine would feel in the deepest part of the ocean on Earth. Okay? The atmosphere is under so much pressure that it's almost a fluid at surface level. Okay? Instead of a gas, it's almost a fluid, and it's all carbon dioxide. So building a spacecraft that can get through this atmosphere without A, burning up, and B, being crushed is extremely difficult. Okay? The Americans didn't try too many landed missions on Venus. They mostly orbited and took like pictures from above. But the Russians were very interested in landing on Venus. So their first mission they sent there, they sent this lander in. It was basically like an armored can. Okay? And when they dropped it into the atmosphere, it got like partway down before it was literally crushed, like you would crush a pumpkin. Okay? Just like that by the atmosphere. Okay, it got hot because of its re-entry through the thick atmosphere, and then the pressure just crushed it. They lost the telemetry early on. So they started building things stronger and stronger, and eventually they did get a few of their probes to actually make it to the surface and survive for about an hour to 90 minutes. Okay? Because imagine you put something that's trying to take measurements and readings, it's a computer, it's got to keep the boards cool and not melt when it's 500 degrees. Okay? So it's very difficult to build something like that. So the Russians finally got a few things to land on the surface. They got pictures of the surface, and then they wanted to take some like sample readings. So they built their probes, like I said, like an armored can, and they had a camera above a mechanical sampling arm. Okay? Now, to protect the camera from re-entry, it had a lens cap. Okay? So the probe landed, okay, and the lens cap popped off. And they started taking pictures, and everybody, like the Russian Prime Minister, all the KGB, because this was back when Russia was communist, right? The Soviet Union. Okay, they were all impressed. They had a very successful mission, and then they were going to take a sample of Venus's surface. Sample arm goes out. What does the sample arm sample? The lens cap. Put the camera right above the sampling arm. When the lens cap popped off, it landed right where the sampling arm would go. You can bet somebody died in a salt mine somewhere in Siberia over that screw up. Okay? That would not have been tolerated in old Soviet Union. Okay? Yeah. So they then improved their probes by having them offset slightly. Okay? And they actually were able to take some samples and get readings and stuff that were sent back to Earth. Okay? Similarly, there's difficulty landing on Mars. but for the opposite reason. On Venus, you can slow down easily because the atmosphere is super thick. Okay? It's survivability that's a problem there. On Mars, there's 1/100th of the atmosphere there is on Earth. It's hard to get slowed down before you become a smoking crater on the surface. Okay? So landing on Mars is actually the difficulty there. Okay? Survivability once you're there is quite easy. We have lots of probes that have survived on Mars for 10 years or more. Okay? And they're able to move around and do whatever because cold is easier to deal with than hot. Okay? But a lot of missions have not survived landing on Mars simply because they don't slow down enough. Okay? There's also this issue with any landing by any probe needs to be done by computer. It cannot be done from Earth. Why not? Yeah, there's a massive delay time. Okay? You've seen the Martian, it's like a half an hour in a best case scenario. Depending on where Earth and Mars are in their orbits, it can be more than that. So you cannot be sending, I think the best case scenario is 10 minutes or something like that. Okay? But you've got 10 minutes for the information to be sent from Mars to Earth. People have to read the information, interpret, decide what to do, and then send the command back. Well, it's 20 minutes. If you're trying to correct that something's re-entry, that's too long. You can't do it. You can't literally fly something, okay, and land it on Mars. So it has to be done completely by computer. If anything happens to the computer, the probe will crash. Okay? Now they've got this down pretty well. Okay? The last probe they landed and the new one that's going, so Perseverance is going, Curiosity is there right now. They use the sky crane. Okay? This ring of rocket engines that lowers the probe. Okay? It just holds there. The rocket engines hold it above the surface. It lowers it by a cable. And then when the cable snaps, the rocket engines fly off. And the thing crashes a long way from the probe, okay, and then the probe lands safely. So that's the new one. They used to use airbags. Okay, the first few rovers and stuff that landed, they'd be in this giant thing of balloons, and they would bounce along the surface. Okay, and that's how they would slow them down. So the balloons would hit and they'd be boing, boing, okay, until they finally rolled to a stop. So all kinds of issues with getting to other places, but gravity can be used as an accelerating force, okay, to get things further away at higher rates of speed. Okay, so we did that already. Okay. Okay, so let's have you guys try these two here. So there's similar calculations to what we did. Okay, they're just using this formula here. Okay, Fg equals big G times mass 1 times mass 2 over r squared. Right, so try 1 and 2. Okay, see if you can do those two. I'll give you a few minutes and then we'll look at them and then we'll call it. All right, so for number 1, okay, the givens that we have are r, 0.60 meters. Okay, so these two people are sitting 0.60 meters apart, which is not social distance. It's way too close. Okay, we should actually change this to like 2 meters apart so it's realistic for today. Okay, person A has a mass of 55 kilograms, and person B has a mass of 80 kilograms. All right, so those are our two masses. There's our separation distance. We always know what G is because it's on our formula sheet. All right, so all we have to do is plug in our numbers. So Fg is going to be 6.67 times 10 to the minus 11 times 55 times 80 divided by 0.6 squared. Important to remember to square that. Right? When we plug that in, we should get 8.2 times 10 to the minus 7 newtons. Is that very much force? No. Okay? That's like the force that, you know, a piece of dust would make falling on your skin. You ever notice that happens? That's pretty small. Okay? You're just never going to notice that. Which is why you don't gravitate towards each other. Okay? On the park bench. Right? Gravity is much stronger pulling you against the park bench than your force of gravitational attraction between the two people. All right? Now, theoretically, if you continue to eat and eat, and your mass continued to get bigger and bigger and bigger, eventually food would come to you. Think about it. Okay? Now, you would be incredibly massive and food coming to you would be the least of your worries at that point because you've probably been dead long before that. But, okay, everyone, I almost always get that question, when would stuff move towards you? When you were close to the mass, close to a fraction of the Earth's mass, say 1/10. Okay? Then stuff would start to move towards you instead of the Earth if you were close to it. Okay, so you could make food slide along the table towards you, maybe. It's weird though. Yeah. All right, how are we doing on number 2? Okay, do we need to go over number 2? Okay, so it's number 2 is just manipulation, right? So we got Fg equals big G times the mass of the iceberg times the mass of the Titanic, okay, divided by r squared, and we are looking for the mass of the iceberg. So I multiply both sides by r squared, I divide by the mass of the Titanic, okay, and big G. Okay, and that will give me the mass of the iceberg, right? So when I plug in all those numbers, I should get 2.0 times 10 to the 8 kilograms. Okay, for that one. All right. If I can have everybody clear off their desktops, I'll come around and spray them, and you can wipe them down for me, please. Oh, I don't know if that's acceptable. I don't think you want to be here that long. Did I get everybody?